I welcome all the students. Today we are going to learn the point under unit number 4, and we have reached to the last point of the unit, okay, that is related to the polygon clipping algorithm. In the last session we have learned the Sutherland-Hogman polygon clipping algorithm. Today we are going to learn the another algorithm which is used for the polygon clipping, and the name of algorithm is Weiler-Atherton polygon clipping algorithm. Weiler-Atherton polygon clipping algorithm was the today's topic of our discussion. Okay, so let us start understanding the Weiler-Atherton polygon clipping algorithm. This is the second algorithm that we are going to learn. The name of algorithm again with the name of the scientist, okay, Weiler and Atherton. Okay, so these are the two scientists. They have shown or they have designed the algorithm which is having the improvement over the Sutherland-Hogman algorithm. Okay, so this is the second algorithm and one of the important algorithm which is used for the polygon clipping. Okay, let us start understanding the Weiler-Atherton polygon algorithm. Before that, we are going to consider what was the drawback of Sutherland-Hogman algorithm. Why there is need to go for the Weiler-Atherton polygon clipping algorithm. Okay, so this is what the point we have mentioned. We can consider this is one of the drawback of Sutherland-Hogman algorithm. See, convex polygons are correctly clipped by the Sutherland-Hogman algorithm. Okay, so Sutherland-Hogman algorithm correctly clips, or it is can be useful for the convex polygon. Okay, but the concave polygons may be displayed with the extraneous lines. Okay, so it means that the Sutherland-Hogman algorithm was not suitable. We underline the word not suitable for concave polygons, and if I apply Sutherland-Hogman algorithm for concave polygons, it may be displayed than extra lines or extraneous lines can be displayed if I follow the procedure of Sutherland-Hogman algorithm. Okay, so that was the reason. Okay, we are moving forward. So let us understand what exactly the problem. Okay, now this occurs when the clipped polygon should have two or more separate sections. Means the polygon which I want to clip having two or more separate sections. It is having two separate sections, okay, or two or more separate sections. Then the problem occurs since there is only one output vertex list. In Sutherland-Hogman algorithm, we are maintaining only a single vertex list, okay, or one initial vertex list, okay, number of vertices we are passing to the left edge, then it is passing to the right edge, and so on. So the same or only one output vertex list is maintained or it is modified. Okay, and due to this, what is going to happen is the last vertex in the list is always joined to the first vertex. Okay, last vertex is always joined to the first vertex, and that may create the extra lines. Okay, so let us understand the drawback that we are having, and now the reason that why we are learning this Weiler-Atherton algorithm. Okay, Weiler-Atherton polygon clipping algorithm. Therefore, we could use a more general polygon clipper. Okay, so that's why we are moving to use more general polygon clipper such as Weiler-Atherton polygon clipping algorithm. Okay, so due to this reason, due to this drawback of the Sutherland-Hogman algorithm, okay, we are going to use the Weiler-Atherton polygon clipping algorithm. Let us understand the drawback or what was the problem with the Sutherland-Hogman algorithm with the help of this example. Okay, so I'm just showing this example or the diagram here. Just look at the diagram. See, the name of the diagram shows, or what we are going to show is clipping the concave polygon. So we are trying to clip the polygon which is concave. Okay, so this is my concave polygon, okay, which is shown in the diagram number A. For this diagram, so this is my existing concave polygon, and for this concave polygon I'm considering this is my window, or this is my clipping window. Okay, now when we go for clipping this polygon considering this window using the Sutherland-Hodgman algorithm, then what we are going to do, then the Sutherland-Hodgman clipper produces the two connected areas in the B. Okay, so it is going to produce the two connected areas in the B, actually in the output. So this is my polygon. Okay, this is the polygon, concave polygon. I want to clip with the help of this window, considering this window as a clipping window. What is my output? My output is shown in the diagram number B, but this diagram is not correctly displayed. I considered it due to, okay, I just connect the same color. If I use the Sutherland-Hodgman algorithm, actually these two areas, okay, these two areas are separate. Okay, but in the Sutherland-Hodgman algorithm, okay, these areas are connected with one line which is going to connect the last vertex to the first vertex, or we are going to connect all the vertices, and generally we are getting this as the output. Okay, so my output is this, okay, which is not a correct output, and generally the result, okay, I getting this as my result. I get the result where the two areas, actually this and this area, this is area number 1, this is area number 2, and actually these two areas are separate, okay, in the polygon. You can find it here. Okay, if I clip it here, this will be separate, this is separate, but unfortunately with the help of our previous algorithm that we call it as Sutherland-Hodgman algorithm, we get one extra line, or we can find that we are having one line which is going to connect these two polygons, okay, and which is not the correct output. So that's why we have mentioned the point, the concave polygons will not be displayed correctly with the help of the Sutherland-Hodgman algorithm, whereas if the polygon is convex, okay, the convex polygons are correctly clipped by the Sutherland-Hodgman, but the Sutherland-Hodgman algorithm does not clip the concave polygon correctly. Okay, so that was the reason we have the next algorithm came into the existence, and it was designed by the Weiler-Atherton. Okay, let us start understanding the improvement that we are having, or which was initiated, or which was developed by the Weiler-Atherton polygon clipping algorithm. Okay, so I'm just moving to the next slide to discuss the Weiler-Atherton polygon clipping algorithm. Now let us start understanding the algorithm. Now in this algorithm means Weiler-Atherton polygon clipping algorithm, the vertex processing produces, or vertex processing procedures, whatever the procedure algorithm we are using, for the vertex processing for window boundaries. Okay, so we are considering for the window boundaries are modified. Okay, so we are making some modification while we are processing the vertex. So vertex processing procedures for window boundaries are modified so that the concave polygons are displayed correctly. So considering the case of concave polygons which are not displayed correctly in the Sutherland-Hodgman algorithm, so Weiler-Atherton algorithm, okay, what it is decided, what it does is the vertex processing procedures for window boundaries are modified. The procedure that we are using in Sutherland-Hodgman are modified in the Weiler-Atherton polygon clipping algorithm so that the concave polygons will also be displayed correctly. Okay, so exactly what we are doing, let us understand this. This clipping procedure was developed as a method for identifying visible surfaces. In the same method, this procedure was developed as a method for identifying the visible surfaces. Okay, so I think we are having in some of the session we learn visible surface and visible lines also in detail, and so it can be applied with arbitrary, okay, or any polygon clipping regions, or arbitrary polygon clipping region. So this method of Weiler-Atherton can be applied, okay, to any polygon clipping regions, and this method was used, or it was used or applicable also to the visible surfaces, to find the visible surface of the polygon, or which are the invisible surface of the polygons when I'm having more than one objects are displayed on my picture. Okay, so this is what the method that we are using. Okay, So continue our discussion. Let us understand the basic idea of the Weiler-Atherton polygon clipping algorithm. Okay, so to understand what is the basic idea behind this algorithm. Okay, now instead of always proceeding around the polygon edges, okay, so generally how we are going to process the vertex, we are following or processing the vertex, okay, around the polygon edges. So we consider here the polygon edges as vertices are processed. Okay, means instead of always proceeding around or instead of always considering the polygon edges, okay, as vertices, sometimes we want to follow the window boundaries or window edges. So this indicates that our Weiler-Atherton polygon algorithm not only consider polygon edges, but it also consider the window boundary edges also. So also it will consider the direction of the window boundary against which we are going to clip the polygon. Okay, so this was the first point that we are having. With paths, okay, with path we follow means generally we can start with the first vertex as v1, then v2, v3, v4. Generally we are going to follow this path. Okay, so which path we follow depends upon the polygon processing direction. So now in Weiler-Atherton polygon clipping algorithm, we are the path that we are going to follow. Okay, so path means we are considering whether I will go for v1 to v2, v3, v4, v5, or I will start from v1 to v5, then v5 to v4, and so on. Okay, the path that we are going to follow depends upon in this algorithm. In algorithm Weiler-Atherton, the path that we are following, it depends upon the polygon processing direction. So we have to consider whether we are going to process the polygon in a clockwise or whether we are going to process the polygon in a counterclockwise direction. So this is considered. The path of polygon processing directions are considered whether I'm using the clockwise or whether I'm using the anti-clockwise. Now what is meant by this clockwise and anti-clockwise? Okay, that's why I'm just going to show. Suppose I'm just considering, okay, my polygon is something like this. Okay, so I consider this is my polygon. Okay, so these are the different edges of the polygon. Now as all of you are knowing, okay, suppose this is my one point, okay, this is my second vertex, this was my third vertex, this was my fourth vertex, getting me, this was my fifth vertex, and so on. Suppose I consider this my first vertex. Okay, and if the polygon processing I does into the clockwise direction, okay, so clockwise direction means I'm considering this as I'm just moving in this direction, which is my clockwise. If I go into this direction, then it is my anti-clockwise direction. Okay, so if I'm using the polygon processing direction clockwise, then from this is one, so I will follow from one to this, so this is my two. Okay, and I will follow this. Okay, so this is my third, then I will move into this direction, and so on. Okay, so this is my clockwise direction. Okay, but if I'm using the counterclockwise direction, then what will happen? My first move after one, I will go to this direction. Okay, this was my anti-clockwise direction. So I will, my processing will be start from 1 2. Suppose this is 2, this is 3, okay, this is 4, and this is 5. Okay, so in the clockwise direction method, in the method of clockwise direction, I will move from 1 to 2, 2 to 3, 3 to 4, 4 to 5. But if I'm having the counterclockwise direction, getting me? If I'm having the counterclockwise direction, then how I'm moving? I will move from 1 to 5. Okay, my processing of vertex will be from 1 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1, and so on. So this is considered in the means the polygon processing direction, whether it is clockwise or counterclockwise or anti-clockwise, that is considered in the Weiler-Atherton polygon clipping algorithm. Okay, now along with this, what we are going to consider is with the pair of polygon vertices, currently being processed, okay, represent the outside to inside pair. Okay, so it has to process represented as, means this vertices that I'm processing, so I have to represent that whether they are considering outside to inside pair, whether they represent outside to inside pair, or whether it represent inside to outside pair. Okay, that we are considering outside to inside pair or inside to outside pair. Now what is the meaning of this? Okay, so for example, I just consider that I just take this as a green. Consider here, this is my window. Okay, whatever I have shown in this diagram with the green color, this is my W, stand for my window. Okay, now for this window, as all of you are knowing, what is mean by outside to inside? And suppose I am moving from the point number 4 to point number 5. Okay, I am moving from 4 to 5. So my 4 point is outside and my 5 point is inside. So this is my outside inside pair, 4 comma 5. This 4 and 5 is my outside inside pair, whereas what is my inside to outside pair? Okay, if I'm moving from the vertex 1 to 2, okay, this is my vertex number 1, this is my vertex number 2. One is inside and 2 is outside. Getting me? One is inside and 2 is outside. So in that case, the pair 1 comma 2, 1 to 2 is comes under the inside to outside pair. Okay, so this, whether I'm considering outside to inside pair or whether I'm considering inside to outside pair, that is also taken into account in the Weiler-Atherton Polygon clipping algorithm. Okay, so all of you understood which are the terms that are considered in the Weiler-Atherton polygon. First thing that we have mentioned in this first point is, okay, instead of always using only the polygon boundaries, we are also going to consider the window boundaries. Second, we are also going to consider polygon processing direction or the path, whether it is clockwise or whether it is counterclockwise, as well as we are also going to consider whether this polygon vertices, whether this pair is going to represent outside to inside or whether it is going to consider inside to outside pair. Okay, so this also we are, so I think these are the three terms or the 3 points that are mentioned here which are considered, okay, in the Weiler-Atherton polygon clipping algorithm. Okay, so let us continue our discussion. I'm just moving to the next slide now to understand this in detail. Now we first concentrate on what is my clockwise processing method or which steps or rules I'm following for the clockwise processing. Okay, so I'm considering now just as an example or just for the method, we are considered that we are processing the polygons clockwise direction. Okay, so just now I have said this is my clockwise direction. Okay, so I will consider from clockwise direction. So clockwise processing of polygon vertices uses the following rules. Okay, what is my rule number 1? Okay, for clockwise processing, for an outside to inside pair of vertices, outside to inside means my first point is outside, second point is inside. Okay, so outside to inside pair of vertices follow the polygon boundary. What we are going to follow is we are going to follow the polygon boundary. Means if my pair is outside to inside pair, if my pair is outside to inside and I'm considering the clockwise processing of the polygon vertices, then we are going to follow the polygon boundaries. Okay, we are going to consider the direction of polygon boundaries, whereas my rule number 2 says that for an inside to outside pair vertices, means if I'm having the inside to outside, for example, one is inside, two is outside, so one point is inside, another is outside. Okay, what we have to do, inside outside pair of vertices, we are not following polygon boundaries, we are following the window boundaries in a clockwise direction. Okay, I think this was the major modification in the Weiler-Atherton polygon clipping, and we have to remember this and follow this to get the correct output. Okay, so what is my rule number 1? For outside inside pair of vertices, generally I think we have referred as it as out in pair of vertices, means first point is outside, second point is inside. So for out in vertices, what we have to follow, we have to follow the polygon boundaries. Okay, whatever the polygon I'm clipping, I have to consider the polygon boundaries. In Sutherland-Hogman algorithm, only the polygon boundaries are considered. But here we are not considering only polygon boundaries, we are also considering the window boundaries. Okay, whatever the window I have decided for clipping, I also consider the window boundaries for what? For an inside to outside pair of vertices. Means my pair of vertices is from inside to outside. In dash out means first point is inside, second point is outside. First point is inside the window, second point is outside the window. Okay, for that what we have to follow? We have to follow the window boundaries, and again also it is in clockwise direction because we are processing the polygon vertices clockwise. Okay, so this is what the rule or the procedure, okay, that we are following for the Weiler-Atherton polygon clipping algorithm. Okay, so let us understand this further discussion with the help of the diagram. Okay, I want everyone to concentrate on this diagram so that the concept will be much more clear. Okay, so first I read what is the description we have written. Clipping a concave polygon, okay, A, with the Weiler-Atherton algorithm generates the two separate polygon areas as is shown in the output. So this my output is correct. This is correct output displayed for the concave polygon. I think we have seen that in the same diagram for the same polygon with the Sutherland-Hogman. I have found that in my output I am having one line. These areas are connected, but actually these are the two areas which are completely separate. Okay, they should not be connected, and I get the correct output in the Weiler-Atherton algorithm. Okay, now how I can say it is correct? What procedure we are following? Okay, let us start our discussion and understand this diagram. Okay, so I just explained in this diagram, this is my polygon, okay, and this is my clipping window. Okay, this is my polygon and this is my clipping window. Okay, see, suppose I am starting, okay, so my starting point is V1, okay, in anti-clockwise direction. I want everyone to look at the diagram and the point that I am highlighting so that it will be easy for everyone to understand. See, this is my V1, correct? This is my first point V1 and this is my second point V2. Okay, this is my V1 and V2. Now, what is this V1 and V2 comes under? The V1 and V2 comes under the rule number 1, outside to inside. My V1 is outside, my V2 is inside. So it will come under out in pair. Okay, so what I have to follow? I have to follow the polygon boundary. Okay, so what is the procedure? As all of you are already knowing, what is the procedure is V1 to V2 that I am considering. So I have to find out the point, intersection point between V1 and V2, that is my V1 dash. Okay, I find out V1 dash. Okay, and now my V1 is not considered, my point will be V1 dash to V2. Okay, so no problem with V1 dash to V2. Okay, it is completely inside in it is drawn. Okay, so means it indicates that this line that I'm having is displayed or it is drawn. Okay, then what I'm having? Then I'm having V2 to V3. Getting me? That I'm having V2 to V3 is considered. Okay, so I'm just going to continue, okay, the discussion. Okay, I'm going to continue the discussion from V2 to V3, this line. Okay, and what is going to happen with this particular line? For this particular line, V2 to V3 is also inside. Okay, I'm having the line V2 to V3 which is completely inside. Okay, so I'm preserving V2 to V3, okay, as per our discussion. Then what I'm having? Then I'm having the line V3 to V4. Getting me? I'm having the line V3 to V4. Okay, so now what is happened with the vertices V3 to V4? Follow the, it comes under rule number 2. Okay, just understand, this is my rule number 2, which is inside to outside pair of vertices. I'm having the inside to outside pair of vertices. Inside to outside pair of vertices because my first point V3 is inside, my second point V4 is outside. Okay, so if I'm finding for any inside to outside pair of vertices, what we have to follow? We have to follow the window boundaries. I think this is what is important. We have to follow the window boundaries. So when I find out my intersection point, okay, look at this diagram. Okay, V3 to V4, this is my intersection point. Okay, and that is I call it as V3 dash. Okay, V3 dash is my intersection point, and this intersection point, after this finding intersection point, I will not go to V4 to V5. I will not go here, but I'm not going in this direction. I will go the direction of I will follow the direction of window boundaries. So what is I'm going to follow? I think you can find it here. The arrow is shown here. And now I am moving into see, this is my window. Okay. So this is my window. Okay. So what I have to follow? I have to follow the window boundaries in a clockwise direction. So I'm moving in this case and I'm going to connect this and this. Okay, so this and this. So I got this to this here. After that, I'm just connecting this because I'm following the window boundary, not the polygon boundary in a clockwise direction. Okay, so I got V3 dash to V1 dash. This point is connected. Okay, after these points are over, then I'm going to resume. Okay, after that we are going to resume with the next vertices that I'm having, that is my V4 to V5. Okay, what about V4 to V5? Again, it is comes under rule number 1, outside inside. V4 is outside, V5 is inside. So we are going to follow this direction and I'm going to follow the V4 dash. Okay, V4 dash is followed, and as it is rule number 1, we have to follow the polygon boundary. So next point I consider V5 to V6. Okay, for V5 to V6, again I'm going to find out the window age. But this V5 to V6 is comes under the rule number 2. And what is my rule number 2? Inside outside pair. I have to follow window boundaries. So after finding the intersection point, you can find this arrow is here. Okay, so I will follow the window boundaries and then I'm going to connect this. So I'm just going to, in my output, I'm going to connect this particular area. Okay, and again this will be continued, and in this way my output that was I'm expecting for a polygon clipping will be achieved, or I'm achieving this result with the help of the Weiler-Atherton polygon clipping algorithm. Okay, Weiler-Atherton polygon clipping algorithm. Okay, we have achieved, or we have followed the correct answer with the help of these two rules and for the clockwise processing of the polygon. Okay, so I hope, see here only the difference that we have to follow. If I'm having outside to inside, then I have to follow the window. This is my window. Okay, I have to consider the boundaries of my polygon clipping window. So that is what I'm having, this arrow and this arrow. Okay, if I'm having inside to outside, I have to follow the polygon boundaries. Okay, so this is what the difference, and this difference has made the Weiler-Atherton polygon clipping algorithm to be useful for the concave polygons. Okay, as shown in our diagram. Okay, so let us continue our discussion and move further about the Weiler-Atherton algorithm. I hope all of you have understood the procedure with the help of this diagram. Okay, let us continue our discussion of Weiler-Atherton. See, there is a possible, or we can say there is a one more improvement. Okay, an improvement on the Weiler-Atherton algorithm is also possible, and that improvement is simply known as Weiler algorithm, which applies constructive solid geometry ideas to clip an arbitrary polygon against any polygon clipping region. Okay, so we are going to consider the improvement in the Weiler-Atherton algorithm, which applies constructive solid geometry ideas to clip an arbitrary polygon against a polygon clipping region. Means my clipping region is now not window. See what I'm saying? I'm not consider window as a clipping window. I consider my polygon clipping region itself is a window. Okay, so that's why we are having the improvement over this. Okay, following diagram shows the same. Let us understand with the help of the diagram here. So I just show the diagram. Okay, so before I go to this diagram, just read the point. For the two polygons in this diagram, okay, the correctly clipped polygon is calculated. Correctly clipped polygon is calculated as the intersection of the clipping polygon and the polygon object. See, my clipping window is not a rectangle window now. My clipping window itself is a polygon. Okay, so you can find in this particular diagram, I just read the diagram description first. Clipping a polygon by determining the intersection of two polygon areas. Okay, now here in this diagram, that is what I told, this indicate, okay, this one, okay, this is my clipping polygon. Okay, so I'm considering here it as my clipping polygon, means my clipping window itself is a polygon. Okay, so I'm just forcing on the point, clipping window is not a normal rectangle, but it itself is a polygon, okay, that you are assuming. And now what we are having, this one is my polygon object. Okay, this is the object. With this object I have to clip against the clipping polygon window. So my clipping window is a polygon window. Okay, I hope all of you understood it. Again, I repeat again, I want to clip this polygon object. I want to clip this polygon object against the clipping polygon window, against the clipping polygon, okay, that we are having. Okay, so in that particular case, you can find that this is my original polygon object and this is my window, and whatever is shown in the blue color, this particular area is my clipped area that I'm having. Okay, so this area is clipped. Okay, the meaning of clipped is this area is not considered, okay, because this is my considered as a clipping window. Okay, so this area which comes under the clipping polygon or clipped area is this particular part, and that is also possible with just a simple improvement with the Weiler-Atherton. So this is what I think it is easy for us to understand how the improvement is possible. Only the improvement is my object is also a polygon, and my clipping window is also a polygon. Okay, so I'm having the original object and this is my clipping polygon. Okay, and then I can find out this is what my area, which is shown with the blue color, is my clipped area. Okay, so this is what we are expecting. Okay, that is what we can say the improvement which is possible, or this is one of the improvement that I'm having in the Weiler-Atherton polygon clipping algorithm. Okay, so this is all about that we are considering about the polygon clipping. Okay, before that we have learned line clipping, and this is we have learned polygon clipping, and under the polygon clipping we have learned the two important algorithm. One is Sutherland-Hogman polygon clipping algorithm, and second is Weiler-Atherton polygon clipping algorithm. Okay, and we have shown in this session that how the Weiler-Atherton polygon clipping algorithm is also suitable for concave polygons, and it can be used for the any polygon clipping. As well as in this diagram we have shown that there is a improvement of the Weiler-Atherton is also possible. Okay, and where I can clip the polygon against my polygon clipping region. Okay, so my window is also a polygon, and that is what's shown in the appropriate in the diagram. Okay, so whatever the concept that we are having for the polygon clipping, okay, can be further extended for the two more points. Okay, so it can be further extended for two more things or two more points. That is what I want to discuss in my next slide. Okay, before concluding the session. Okay, so let us understand the next point. See, whatever we have learned, okay, whatever we have learned for the polygon clipping can be applicable, can be also useful for curve clipping as well as the text clipping. Okay, so it is applicable to the curve clipping as well as and the text clipping. Okay, so let us understand the first about the curve clipping. Okay, so I'm just considering that the polygon clipping is extended further for the curve clipping as well as for the text clipping. Okay, the areas with curved boundaries, the areas with curved boundaries can be clipped with the methods similar to those of Weiler-Atherton algorithm. So that is what I told, the Weiler-Atherton algorithm can be further improved or can be useful for the curve clipping also, the area with curve boundaries. You can just look at this particular diagram, clipping a filled circle. Okay, so this is my clipping window. Okay, you can find this dotted line indicate this is W, means my clipping window, and this is my object, which is a circle, filled circle. Okay, my object is filled circle, and after clipping this filled circle with the help of the clipping window, what is my output that I'm getting? This is my output. Okay, so this is because this is the part from this to this, you can find that this is the part which is inside the clipping window. Okay, so I get this is the part which is inside. Yes, you can find it here. This to this is my window, and this is the part of the circle, and this is my expected output or the correct output. So this particular point indicate that how I can extend this for the curve clipping algorithm. Okay, not only for the field color, rather, okay, the field curve or field circle that I'm having, and how it can be clipped. It can be shown, visualized easily with the help of the diagram. Now this can be further extended for the text clipping also. Okay, so that's why I have mentioned this point. It's also applicable to the text clipping. It is also applicable to the text clipping in graphics packages. Okay, so this can be further extended. Now, what was the method for the text clipping? So I just have mentioned one method here. The simplest method for processing the character string relative to a window boundary. So I just want to clip the text also or the string also. So the simple method is used is to all or none string clipping strategy. Okay, so what is the method is all or none string clipping strategy. Means if the string is completely inside, then preserve it. If some part of the string, okay, some part of the string is inside, some part is outside, so completely remove that particular string. Okay, so this strategy is known as all or none string clipping strategy as shown in the diagram. Let us understand the diagram. See, this is what the diagram that we are having. Okay, so this shows the text clipping also. The text clipping using a bounding rectangle about the entire string. Okay, so you can find that here the string 2 is completely inside the clipping window. So this is my clipping window. Is my string number 1. So sorry, string number 2. This string 2 is completely inside, so it is displayed on the screen. In after clipping, it is displayed. But what happens with the string number 1? You can find that the string number 1, some part of the string is inside, some is outside. And if I clip this part, I will not get the complete string. Okay, I will may get the word str will be outside. I just get ing1, and user will not understand what is this ing1. Okay, so what is the method under the text clipping suggests? All or none. Means if the complete part of the string is inside, then you have to preserve it. If some part of the string, okay, so I consider this is my string, and this some part of the string is outside and some part is inside. In that case, that part, this completely string is removed, and you can find it is not displayed here. Okay, in the after clipping, that particular string was not displayed over here, and this strategy is known as all or none. Means if you keep the complete string, else you clip the or don't do display the string itself. Okay, because the part of the string will be inside, some text will be inside, some text will be outside, and it will be difficult for the end user to understand what is the complete string. Okay, because we are keeping some part of the string. Okay, so the method generally they use is all or none string clipping strategy is used, and that is what is shown over here. Okay, so this is all about the, that is what I told. Why I have added this particular point is so that we can understand that whatever the Weiler-Atherton algorithm that we have used, that can be further, okay, extended not only for the polygon clipping, it is further extended for the curve clipping, as well as it can be further extended for the text clipping. Okay, so that's why we have learned the point curve clipping and the text clipping also. I hope all the students have enjoyed the today's session where we have learned the Weiler-Atherton polygon clipping algorithm in detail. Okay, so we have seen all the details of this algorithm, and hope all of you are having the happy learning. Okay, so we end our session, today's session here. Okay, thank you all the students, thank you all.